Okay, so this is going to be Freefall video number 2, and it's going to be all about equations this time. We're going to talk about what equations we can use, how we can use them, and an equation that we definitely are not going to want to use with Freefall. So we'll start off with an example. Let's say we had an object and it started at a certain height, and let's say it falls down to the ground and it's maybe 10 meters high. And we want to know how fast is it moving when it gets here. So how fast is it moving when it hits the ground? Now, one way to think about this would be, let's say this is real life and we can time how long it's in the air for. So we know the time. And maybe we try to bust this equation out. We use this a lot. V equals d over t. We have that 10 meters and we have that total time. The problem with that is that this equation is going to tell us the average speed for the entire time the object is in the air. It's not going to tell us the speed at any particular point. So a good rule of thumb is that we don't want to use this equation when an object's speed is changing. And for objects in free fall, their speed is always changing. So these three equations on the back of our reference table are going to be very helpful. And this one, hopefully, if you remember from back when we did acceleration, the other two are going to be new, but they shouldn't be scary at all. And we'll do some examples with them. The first example we have here, we can actually use this last equation for. This VF squared equals VI squared plus 2AD. A is just our acceleration, and D is the displacement from where it started. And the way I figure out which equation to use is by making one of these tables and just identifying what I have on the other side of this, and then figuring out what equation I want to use that way. And when you make these tables, you don't have to memorize the five quantities. What are the five quantities? They're just the five things that you see in these equations. We see VF, we see VI, we see A, we see T, and we see D. So those are the five things that I want to put here. And I can start to fill this out. This object started at rest because it dropped. So its initial speed was 0 meters per second. Now, I don't know its final velocity, but that's what I'm looking for. So I don't want to just leave that blank. I want to indicate that that's the thing I'm looking for. So I put a question mark in there. Now, I'm not given an acceleration at any point necessarily, but I know this is an object in freefall. I know every object in freefall accelerates at 9.8 meters per second squared. Now I know the distance it falls is 10 meters. Now, I can get to the last one. Time is not something I'm given. It's also not something I'm looking for. And that's actually going to be the key. So I'll call that sort of the key quantity. Now, what's really helpful is by identifying this time as an equation or as a variable that I don't have, but I also don't necessarily need, is that it tells me that this equation over here that doesn't have time in it is the one to use. Anytime you can identify a quantity that you don't have and you don't need, you want to use the equation where you don't have that quantity. For example, this equation in the middle here, this d equals vit, you'll notice it doesn't have final velocity. So if that final velocity was the key quantity, I would want to use the d equals vit equation. Let's say displacement was the key quantity. Well, this equation at the top that I've highlighted in yellow, well, that doesn't have displacement. So whether it's going to be one of those three, time, displacement, or final velocity, and figuring out which one it is going to tell you which equation to use. So the next thing that I want to do is I want to state that equation to indicate which equation it is that I'm using to solve this problem. The next thing I want to do is substitute the numbers I have into that equation. I wanted to be careful. You'll notice I didn't forget to put my units here on my substitution. That's an important thing to remember when we do physics problems. Now I can do some algebra. I can get rid of this 0 here, and I can take the square root of both sides of that equation. Now you might have been worried there for a second that we were going to try to take the square root of a negative number. It turns out that that 10 meters per second, or that 10 meters here that it goes down, because it's going down, and this is a displacement, that's also a negative. So we're going to be doing a negative times a negative, and that's going to go away. And you can punch that into your calculator. And you should get a speed at the bottom here of 14 meters per second. All right, I just want to do another very similar example as well. Let's imagine we had a dropped object, but instead of knowing how high up it was, let's say we knew how long it was in the air for. So we measured that one this time. Let's say it was in the air for 2.5 seconds. Now we're going to approach this problem the same way. We're going to fill out our table here on the side, and we're going to figure out what equation we want to use. So it is still dropped from rest, so its initial speed is still 0 meters per second. We're still looking for this guy, so we're going to put a question mark in there. Our acceleration is still negative 9.8 meters per second squared. Now this time we don't know the displacement and we don't care about it. We're not looking for it yet. So that's going to be our key quantity. And we know the time is 2.5 seconds. Well, if the displacement is the key quantity, this is the equation that we're going to want to use. So let's start off by stating that equation. Let's plug in our numbers with units. And now let's punch this into our calculator. And I got 24.5 meters per second. The last thing I want to talk about is you can actually use these equations to study gravity on other planets. Gravity is going to work the same way. It's going to pull all objects down at the same rate, whether you're on Earth or you're on the moon or you're on another planet. It's just that the acceleration that it pulls things down at is not going to be 9.8 meters per second squared. So let's say we were on the moon or something, or a different unknown planet, and we knew an object was dropped, we knew how long it was in the air for, and we knew how long it fell, and we wanted to find the acceleration on that planet. And I'll make up some numbers and I'll fill it in, and we'll do that as an example. So it starts out at rest, 0 meters per second. Now this time we don't know the final velocity and we don't care about it. So that's our key quantity. Our acceleration, that's our unknown. So we're going to put our question mark in there. Our displacement, let's say it falls 10 meters and it takes 3 seconds for it to do that. So VF is our key quantity here. So we want to choose the equation that doesn't have VF in it, which is this one. And we're going to start off by stating that equation. We're going to plug numbers into that equation with units. Anything times 0 is 0, so I can cross off this part, and I can multiply both sides by 2, and I can divide both sides by 3 seconds squared. And I can punch that all into a calculator, and I get an acceleration of 2.22 meters per second squared. Thank you for tuning in. I know that was a little bit of a longer video, but I hope it was helpful.